Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll finish our module on sequences by covering the concepts of limit superior and limit inferior of a sequence. Last time we discussed the notion of a Cauchy sequence and showed that the notion of a Cauchy sequence is same as the notion of a convergent sequence. So what was a Cauchy sequence? A Cauchy sequence is a sequence where for every epsilon greater than 0, after the first few terms, all the remaining terms of the sequence are at most epsilon distance from each other. So that was the Cauchy sequence, and we noticed, or rather proved, that Cauchy sequences are convergent and convergent sequences are Cauchy. These are the problems for today. And now let us get on with the material of this lecture. So what is the notion of limit superior and limit inferior? So we start with the real sequence. So let xn be a sequence in R. And using xn we define two new sequences. Define two new sequences or two sequences. One is an, which is obtained by taking infimum of all terms on and beyond n, and another is bn, which is obtained by taking supremum of all terms on and beyond n. So just some definition, and note that this is an increasing sequence and this is a decreasing sequence. Very simple observation. Also, an is at most bn for all n. So with this fact in hand, we know that this expression has a value, either it is finite or it is plus infinity. So when it is finite, that means the sequence converges, this particular sequence converges. If it does not converge, then it approaches infinity. It just keeps on increasing and becomes larger and larger, in the sense that it becomes larger than any positive integer. So this quantity exists, and I shouldn't say exists, but this is either a real number or it is infinity. And this is called the limit inferior of xn, and is written as, this is a notation, so we have defined limit inferior, and similarly we have this guy also is either infinity or a real number. Sorry, not infinity, either minus infinity or a real number, because this is a decreasing sequence, and this is defined as, or rather this is called the limit superior of xn. The notation is naturally lim sup. Okay, and if we just look at this, we will see that the limit inferior is at most limit superior. This is true for any sequence, with the convention that any real number. So what's a good, okay, so r is less than equal to infinity for all real numbers, and minus infinity is less than equal to infinity, infinity less than equal to infinity, minus infinity less than equal to minus infinity, and minus infinity is less than equal to r for all real numbers. So with these conventions, the above makes sense. Okay, so let me just quickly give two examples. So first example is define xn equals n for all n. Then what is an? An as defined above is just n, and bn is infinite. So lim inf of xn is infinite, and lim sup is also infinite. So that's one example. Let me give another example. So this time we take our one of our favorite sequences, which is xn equals minus 1 to the n. So then an would be minus 1 constant and bn is plus 1 constant, and therefore the limit inferior is minus 1 and limit superior is plus 1. So limit superior and limit inferior may disagree, or they may agree. Anything can happen, but this will always be maintained. Alright, so now let us see how this notion correlates with the notion of convergence. So here is the theorem. Let xn be a bounded sequence. Then xn converges if and only if the limit inferior is equal to the limit superior. So very nice theorem, but the proof is of course not very hard. This should be, you can take this as an exercise and then look at the proof that I'm about to write down. So we start with a convergent sequence. So let xn be a bounded sequence, and then we assume the hypothesis, the bounded sequence. And now first assume that xn is convergent. Well, if something is convergent, then it is automatically bounded. So, but anyway, redundancy is fine. So we started with the convergent sequence, and now we want to show that these two quantities are the same. So let epsilon greater than 0 be arbitrary. Okay, so by the fact that xn converges, before that let me say x equals the limit of xn. Let's just introduce that notation. So now, since this is the case, for each epsilon greater than 0, there is some n, some natural number such that xn minus x is at most epsilon if n exceeds capital N. So this implies that x minus epsilon is at most xn is at most x plus epsilon if n exceeds capital N. And now if we take an, as we defined earlier, is the infimum of all terms on and beyond n, then an is greater than or equal to x minus epsilon for n greater than or equal to capital N. That's immediate from this line. and this implies that the limit inferior of xn, which is by definition the limit of an, this is at least x minus epsilon. And similarly, the limit superior, by a very similar argument, of xn is at most x plus epsilon. So we have these two things with us, but now using the fact that this is at most that, we see that x minus epsilon is at most limit inferior is at most limit superior is at most x plus epsilon. So this means since epsilon was arbitrary, this implies that these two quantities better be equal. So we have proved the first part of the theorem, and now for the other direction. Now assume that these two quantities are the same, meaning the limit inferior and the superior are the same. And call that x. And we will show that the sequence converges to x. So this is what we will do, and that will finish the proof of the theorem. So to do this, we fix epsilon greater than 0. And by these statements, there is some n. So then there is n. Some natural number such that I'm just using the definition of limit inferior as well as the fact that this is equal to x. So what we get is this is xk. This becomes at most epsilon, as well as at the same time this also becomes at most epsilon if n exceeds capital N. So that is immediate from this statement. Alright, but note that. So let me put this in a box. Okay, so now you observe that infimum of xk, k at most n, is of course at most xn. This is true for any n. And this implies that x minus infimum k greater than or equal to n, xk is at least this much. And similarly, by the very similar reasoning, we get this is at most x minus xn. Alright, but x minus, so alright, so let us combine these two things and write that in a single statement. So what we get is x minus supremum k greater than or equal to n xk is at most x minus xn, which is at most x minus infimum k greater than or equal to n xk. So we just rewrote this thing. And now note this step. This is greater than x minus epsilon, and this is less than x plus epsilon if n exceeds capital N. So let me justify this. If n exceeds capital N, then we have this inequality, which immediately leads to that. because we have an inequality in the absolute value. Sorry, this is the supremum part. So here we come here. So when n is greater than or equal to n, so using this, since this is in the absolute value, we see that this quantity cannot be what have I written? This is minus epsilon. My bad. This is minus epsilon, and this is plus epsilon. Yeah. So once again, I want to justify that for little n greater than capital N. How do we do that? We have this for little n greater than capital N, but this immediately leads to that because we have this in the absolute value. So that's the justification for that. And similarly, this justifies that. And therefore, minus epsilon is less than or equal to x minus xn is less than or equal to, not less than or equal to, this is a strict inequality because these two, this is not strict, but this is strict, so this also becomes strict. So this is less than epsilon if n exceeds n, which is another way to say that x minus xn is at most epsilon if n greater than or equal to n, and this is the same. Since epsilon was arbitrary, this means that xn converges to x and then approaches infinity, and that's it. That's the end of the proof. So for any convergent sequence, the lim sup and the lim inf agree. And if the sequence is bounded and the lim sup and the lim inf agree, then the sequence is convergent. So a very nice fact. And yeah, I guess that's it. This ends our module on sequences. Our next module will be about open sets, closed sets, compact sets, very important concepts. But then when we have all that on our table, we can talk about continuous functions, which is really where the real action starts. So far it might feel like a bit boring, over and over we are just giving more definitions, but when we talk about continuous functions, then things will become much more interesting. Alright, so as usual, like, comment, share, subscribe. I also have Patreon, the link is in the description below. Thank you for listening, and I'll see you next time.